Hello, everybody. All right. So before we get started, a couple things. First of all, there is no class on Thursday, as I'm sure you are aware. So do keep that in mind. And because of that, this is going to be our last class before your first term test. So if you do have any questions about it, now would be a great time as I go to the actual slide. There we go. That's your class. If you do have any questions about it, now would be a wonderful time. But most importantly, keep an eye out for your email over the next few days. There will be some more information and some more reminders coming your way. It's nothing that isn't already on the course outline, but just, some reminders over the next couple days in terms of what to expect for your term test in your next tutorial. So yeah, so I'm happy to answer any questions if anybody has them. There is a question on your screen, so feel free to get started with that if you don't have any questions, but I will take some time now to answer any questions that people have. Yes, you would upload the answers and take pictures, and you'd upload it onto CrowdMark. Yeah, so just like the honesty declaration, and I am assuming everybody here has done it because I've done nothing but annoy you with reminders about it. So yeah, so just like you did for the honesty declaration, you would do the same thing for the term test. Do you need 1 page per question? No, you don't need 1 page per question, but if you do multiple questions on the same page, then you'll need to upload that page to both answers. So if, let's say, you answer question 1 and question 2 on the same page, then you upload your solutions to question 1 and also to question 2. There's 3 questions, I guess. Do you need to print the test? No. You can just write it. So you do what you did with the honesty declaration, where you got the email from CrowdMark, clicked on the link, and it sent you to a page where I think you have to log in or something, but then it sends you to a page. You'll see the questions. You can write your solutions on paper, snap a picture and upload it, or scan it and upload it. Whatever you did for the honesty declaration, do that. That's half the reason why we did the honesty declaration. Yes, you'll need to have your cameras on. You'll need to be present in your tutorial. Anybody who does not show up in your tutorial will get a 0 on the test, regardless of whether or not you answered stuff. Well, if you if you upload your answers to your test but you weren't in the tutorials, it'll just be an automatic 0. You need to be in your tutorials. Yes, you can do your exam on an iPad or do it digitally if you're comfortable doing that. If you can do it as quickly as you could do it on pen and paper, that's perfectly fine. Then just save it as a PDF and upload that. That would be perfectly fine. More and more people are comfortable with that, doing that as quickly as pen and paper. So, save some trees, I guess. The test goes from 1.1 to 1.3. You're allowed your lecture notes, yes. The TAs would watch you. So your TA from your first couple tutorials, it'll be that same TA, so it should be someone that you know. Or know, how much can you know somebody that you're only seeing over Zoom or over WebEx? But it'll be your TA who's watching you. No, there's not a lockdown browser. Unless people piss me off so much with academic dishonesty issues that we have to start doing it. But I'm hoping that's not going to be the case. Sorry, I've already busted 3 people for academic dishonesty this term, so I'm already cranky about it. Not this class, though. What will you be permitted to use during the test? Read on the course outline. It has a detailed breakdown. I'm going to balk on that question.
just because I don't want to say anything that contradicts what the course outline says. So if you've done your honesty declaration, it says it right on there. But also read the course outline. That way I won't forget anything if I'm just saying it now. Yeah, if you can do it faster on your iPad, then use your iPad. That's perfectly fine. Yeah, PDFs will work, photo files will work, all those things you can upload to CrowdMark. So either way. Can you upload questions as you finish up? You have 20 minutes to do the test. When those 20 minutes are done, you're done. And then we give you some time afterwards to upload. So if you are uploading as you finish them, there's no rule against it. But then you're taking time out of your 20 minutes that you're allowed to write to be uploading things. So no rules say you can't do that, but you're not going to get extra time at the end because you spent time uploading. Section 1.1 to 1.3 is on the test. Questions will be on CrowdMark, just like during the thing. Yeah, so you can only use your phone to do uploading, snapping pictures. You can't be on your phone during your test, but you can definitely have them both. And I would assume the vast majority of students will be using their phone to upload. As I said before, 3. I think I got everybody's questions. Struggle with proofs, do you have any tips about it? Try the practice questions and the suggested exercises. Let me know if you're struggling with them. I mean, in general, when you're working with proofs, I mean, if you don't know the definitions of the things you're talking about, then you're going to go nowhere. You're going to go nowhere with proofs. If I say show something an inverse and you have no idea what an inverse is, then it doesn't matter how good you are with proofs or how bad you are with proofs, you're going nowhere. So the first things and the thing that students struggle with, mostly when it comes to proofs, is not actually knowing what the terms mean. So while we don't directly say, define this, define that, I mean, I'm not saying we won't, but we don't normally. If I say, show this thing is invertible, and you have no idea what it means to be invertible, then, there's a problem. So I would definitely suggest knowing what the terminology means is certainly step one. And honestly, for most students, that's enough to get going and do most of the proofs that we would see in this course. Is just knowing what things mean. But if, and I'm not targeting any students here, so I'm not targeting the person who asked the question. It's a great question. But students tend to think of, oh, I can do all the calculations so I know what I'm doing, and don't bother learning what things mean. And then you might as well just write 0 on any theory question that's going to show up. Lecture notes is on the list of things that you're allowed. But I mean, looking at the course outline and seeing here, because I think there's like 4 things. Here are the 4 things you are allowed. And your lecture notes are on there. Yeah. I think I just said your notes, but lecture notes would qualify under that. Anything taught in the course, anything done in the videos or in the sections we've done is fair game. Is there an online textbook you can use for practice? Maybe. We're not corresponding to an online textbook. It's quite possible that I'm sure there's some open education resources out there that you can look for, but I don't have any specific one to tell people. Yeah. If it's on the list of things you're allowed to use, then yes, you're allowed to use them. Yes. Yeah, in the course outline, every section has a list of suggested exercises there. I think I got everybody's question. Feel free to fire them off. This is important. It is important that everyone understands what the tests are going to be like. I'd much rather have these questions now
than emails of people begging for forgiveness when they don't know what happened afterwards. So. The exact timeline is on the course outline. I think it's 7 minutes to upload. So 3 minutes to check student cards, 20 minutes for the test, 7 minutes to upload. But if there is a difference between what I just said in the course outline, then it's what the course outline says. It's in your tutorial. The upload file does not have to be a PDF. It can be a PDF, but JPEGs or pretty much any picture files also work, is what most students would be doing. Any type of photo identification would be fine. I'm going to say no for using your phone for notes, because then it looks like you're doing other things and communicating with other people. I mean, if you want to use your phone for notes, that's okay, but you better have like the notes on. If you're scrolling and playing with your phone throughout the test, then that's going to set off red flags. I mean, if you have your phone just sitting there and you're looking at it and that's all that there is, that's not going to be a problem. But if you're constantly scanning and stuff throughout your phone, then that's going to set off some red flags for the invigilator. The tutorial, the test is in your tutorial.
I'm sorry for interrupting, but by saying the tutorial, you mean the lab section?
Yes, lab, tutorial, whatever B blank blank that you've been going to either on Monday or Friday, depending on which one you signed up for.
Okay, thank you.
Welcome. Does it make linguistical sense? Does it say A times B equals does not exist? Does that make sense in terms of English? Or does it say the answer doesn't exist? Whichever one makes more linguistic sense is what you should do. No, it doesn't. All right. So, all right, this is the 5th time people have answered. How many questions are there? I've answered it 3 times. I'm good with that. So let's get this started right here. So we have a matrix. We want to show that A inverse is equal to this right here. How do we show? And again, part of today's class is we're going to develop a method for finding the inverse, but we're not there just yet. So how do we show that something is an inverse of another matrix? What does it mean to be the inverse? Right. What it means to be the inverse is that you multiply them together and you get the identity. So that's what it means to be the inverse. So if we're checking this, that's what we're going to check. So 3, 1, 2, 5. So in order to be an inverse, do you have to multiply it on the left or on the right in order to be the inverse? Both, exactly. You caught my trick question. So it's got to work on both sides. Can I just factor out this 1 over 13 and bring it in front, or does that violate the rule of switching the order of multiplication? Right, it's a constant. It's a constant, so yes, you can bring it out in front. And then we can multiply it together. So 3, 1, 5, negative 2. That's going to be 13. 3, 1, negative 1, 3 is 0. 2, 5, 5, negative 2 is 0. 10 minus 10. And 5, or 2, 5, and negative 1, 3 is negative 2 plus 15, which is 13. And so we get 1, 0, 0, 1. So we get the identity just like we want, but as some people have mentioned, you got to multiply on the right-hand side as well. Why do we have to do both? Why isn't it just true that if one of them works, so does the other? At least at this point. Maybe we'll prove something about that later. I would say that I would expect students to know that that's I. Yeah, because multiplication is not commutative. We don't know for sure going into this. Now, that is something that we might want to try and prove. But based on what we have right now, there's no guarantee that matrix multiplication is going to work and get the identity the same thing on both sides. That being said, we are eventually going to see why that's true. But for now, just getting our feet wet with all this inverse stuff, we don't know that for sure. All right. Any questions about how we could verify something is the inverse? It doesn't really tell us where this thing came from, but it does tell us how we can verify something's the inverse. Any questions about this one? Indeed there is. Indeed there is. Yeah. All right. So someone said for a 2x2 matrix, isn't there a shortcut? Yes, there is. So if you remember this example right here that we did on Thursday of last week, we saw that this one didn't work because, and we saw that it had something to do with the fact that the second row was a multiple of the first. So that's kind of wrapped up in this statement right here, which I've been told, I had a typo in the pre-lecture videos and actually said equals instead of not equals. So as long as this little calculation is not equal to 0, then the two rows won't be multiples of each other. We won't get a redundant equation. And there's actually a little bit of a formula that I encourage you to verify on your own that would say 1 over that little calculation. And then some people were saying the diagonals switch and the off-diagonal entries become negative. And, this is a formula that we could prove is true. So this formula does work for 2x2s. It doesn't work when you go beyond 2x2s, or at least it doesn't without getting much more complicated. So it's perfectly fine for you to use this for 2x2 matrices, although throughout today we'll talk about a method that works for bigger matrices. All right, so any questions about either this formula? If you plugged in the numbers 3, 5, 1, 2, that's where you're going to get the 1 over 13 from. But any questions about this or how we can verify something? All right, I'm going to put a pin in talking about the determinant just because that's something in chapter 2. We're a little bit away, so I don't want to spend a lot of time talking about something we haven't talked about yet. But I mean, the answer to your question is yes. But we'll get to determinants a bit later. How would we go about that? That's exactly what we did right here. This was verifying that it was the thing. So if you're talking about verifying the formula, you would just do the exact same steps we did for this question. You would just do it generally with the letters and show that you get the identity for any of these letters versus the specific ones we did our example for. If you have any more questions, feel free to keep firing them off. If not, give this one a try. So you'll notice that I've been saying words like an inverse as opposed to talking about the inverse. And that's because technically we haven't shown that a matrix has one and can't possibly have more. So see if you can show that if there is an inverse to a matrix A, show that there can't be more than one. Right? Show that there can't be more than one inverse to the same questions. That's some mathematical philosophy right there. So the constant there doesn't matter when finding that inverse. I'm not sure what you mean by that. I mean, the constant definitely matters. If we didn't put 1 over 13, we wouldn't have got the identity. We would have gotten 13 times the identity. So I'm not sure what you mean by the constant didn't matter. So we had to do both. For now, we have to do both. But it's possible after we show this thing that we might not have to do both. All right, so hopefully you've had a chance to, maybe get started on some of these things. So this is what I was talking about before, where we kind of need to know what it means. So if A is invertible, we want to show that there is just one inverse. How do we show that there's only one of something? There's actually a few ways, but how can we show that there's just one of something? Two of what? That's true, but we want to be a bit more specific. Two of what would be the same? There we go. So if we want to show the inverse, if it exists as unique, the idea is that if B and C are both inverses, then B has to be equal to C. It's impossible to get two different inverses. So if B and C are both inverses, they can't be different. They have to be the same. So all we really need here is what it means to be an inverse. Right? So what does it mean to be an inverse? So if B is an inverse, what does that mean? B equals I? I don't think that's what you meant. Right, so AB is equal to the identity matrix. Beautiful. Anything else? We can't use the equation from before because nothing about this said that we're dealing with 2 by 2 matrices. AB is equal to I. Do we have any other information? One more piece of information we have. Yeah, B times A is equal to I. We can use either side. Similarly for C, since C is an inverse, AC is equal to I, and CA is equal to I. So this is what I was talking about before with the excellent question that somebody asked about proofs, is that we need to know what it means. If you're immediately jumping to a formula, as opposed to asking yourself, what does it mean to be invertible, then you're already going to get stuck on a theory type question like this. You need to know what it means to be an inverse, not just, oh, what formula can I plug things into is not going to help you here. All right, and we want to use these things and maybe some of the other properties to show that B is equal to C. All right, so let's do it. Can anyone see a way of taking these equations and to show that B and C have to be the same? Equate what? You want to start with AB equals AC? Okay. So AB is equal to I, which is equal to A times C. Okay? I'm not saying this will work, but let's just get some ideas out. I mean, it might work. So this says AB is equal to AC. I'm not disagreeing with that. What do we do with it? I don't know what A negative 1 is. Is it B? Is it C? Is it some other thing? Even saying multiplying by A inverse is implying that the inverse is unique. We're finding that one, which technically don't have it yet. But that doesn't mean that it's right. The idea is certainly not wrong. So I don't know what 1 over A means. I mean, people saying multiply by the inverse. The only issue I have with that is the word the. I know you're not writing. I mean, you're implying that you're using those words. If anybody's writing A inverse, you're saying the inverse. And I don't, we don't have the inverse. We have a inverse. So what can we multiply to get rid of the A? So the idea is we want to get rid of this A, but we can't divide by it. Some people are saying multiply by the inverse, so what are our potential inverses here? Yeah, exactly. So we could multiply by C on both sides. Again, being very careful, we're multiplying on the left, and there's nothing special about C here. We could have done the same thing with B. But I want to multiply C by A, but A is inside a bracket attached to the B. Can I just move the brackets around? Sure, absolutely. That is allowed, as long as you're not changing the order. As long as you're not changing the order of multiplication, you can do that. What's CA equal to? That's I times B is equal to I times C. And so B is equal to C. All right. So there we have it. So if there's an inverse, and that's a big if, we've already seen examples of matrices that don't. But if there's an inverse, then there's only one. Because if we had a second one, we could just show that it was equal to the first one. All right. So the idea behind this is that we can just multiply by the inverse. I can use that word now. We can multiply by the inverse because there is only one. There is only one inverse if there's one at all. There might be zero, but there can't be two. All right. And if we have a 2 by 2 matrix, then we have a formula for it and a rule that tells us exactly when we get an inverse. Obviously, beyond 2 by 2s, things get a little bit crazier. Okay. So, any questions about when we have an inverse for 2 by 2s or the fact that we just get one? So, give you a couple minutes. So we're going to finish off section 1.4 by just talking about a few little properties of the transpose and the inverse. So here's a property for the transpose. So feel free to give that one a try. This will be very similar to our distributive property thing, where we had to verify two things about both sides of that matrix. I know I don't post my OneNote files. I don't see why the distributive property would work here. I mean, I guess I can't rule it out. I'm not thinking of a way that it works. Yeah, I can't see how it would work, at least not directly. I mean, there's no multiplying over addition here, so you'd have to be very creative to even make the distributive property make sense here. When I said it was like the distributive property, I said we had proven on Thursday we showed the distributive property was true. So what I was meaning was the ideas we did there, we're going to use similar ideas here, not that we're going to directly use the distributive property to do it. But since we're already talking about it, that's not a definition. This isn't a definition. This is a consequence of the definitions of transpose and matrix multiplication. Yeah. So it's a property that we're trying to show. All right, so how do we do that? We saw lots of properties. We showed a couple of them earlier. So what do we need to show in order to show that these two matrices are equal? There were two things we needed to show. Show they have the same size. Show they have the same entries. Same size and same entry. So let's start with the size. So what size would A and B have to be in order for that left-hand side to be defined? And order of operations is true here. We would do A times B first before taking the transpose. So what would have to be true about A? And what would have to be true about the size of B? And no, I'm not just saying A is a matrix. So what is the size of A and the size of B? Yeah, so A would be an M by R, B would be an R by N. So the number of columns of A have to match the number of rows of B in order for A times B to be defined. Why does B have to equal N? I don't see a reason why B, M, and N have to be the same. Okay. So if A is M by R and B is R by N, then what is the size of A times B? I know you can take the transpose of any size matrix. It doesn't have to be square. So A times B is an M by N matrix. So what is the size of A times B transpose? All right, it would be N by M matrix. So AB would be M by N. The transpose would flip the rows and the columns. So N by M. All right, beautiful. So that's our left-hand side. Let's move to our right. What is the size of B transpose? What is the size of A transpose? Using the same A and B that we had above. What would be the size of A transpose? What would be the size of B? So A would be R, or I guess I switched the order. B transpose would be N by R. A transpose would be R by M. So what happens when we multiply them? That's right, N by M. So exact same as what we had up here. Their sizes are exactly the same. All right, so we show the sizes are the same. Is A times B N by R? No. I don't think so. No. A was M by R. So A transpose would switch the rows and columns. The rows and columns of A. That would switch the rows and columns of B. Yeah, I did B first because it went first in the product. But, I mean, the order in which we write them doesn't really matter. All right, so as for the entries, we have to look at the ith row, jth column entry of A times B transpose. So what is the ith row, jth column entry of A times B transpose? Right, it would be the jth row, ith column entry of what? Jth row, ith column entry of AB. Beautiful. So we saw some examples of this before. So for transpose, you're just flipping the rows and the columns. So if you were in row 2, column 3, now you're in row 3, column 2. You're just switching the row and the column. So now we're dealing with multiplication. So this was the bit more confusing one, although we saw examples before. If we want to find the jth row ith column entry of A times B, how do we find that? How do we find the jth row, ith column entry of A times B? Right. We take the jth row of A times the ith column of B. So the jth row of A gets multiplied by the ith column of B, and you can do the whole entries thing, although I'll leave it right here. We take the jth row of A and multiply it by the ith column of B. So that's kind of the opposite of what we did for AB, where J was the column and I was the row, but that's because we're doing the transpose. So that's why those two got flipped around. Right. So that's our left-hand side. As for our right-hand side, that's B transpose A transpose, the ith row, jth column, which means that would be the ith row of what? Times the jth column of what? So this would be the ith row of B transpose times the jth column of A transpose. That's how we multiply. We take if we want the fifth row, seventh column entry of a product, we take the fifth row of the first matrix times the seventh column of the second matrix. That's what we've been doing since the first time we multiplied matrices together. Of course, what is the ith row of B transpose? What is the ith row of B transpose? It's the ith column of B, and the jth column of A transpose is the jth row of A. And unless something went crazy, I certainly hope that these two things are equal. And if we look at them, they are absolutely equal to each other. So that's our left-hand side. We showed their sizes were the same, we showed their entries were the same, and therefore it's the same on both sides. And if you remember, we did, when we did all those examples of matrix multiplication and transpose and trace, we did an A times B. We took its transpose, and I told you that it would be I suggested that you find A transpose and B transpose and multiply them together and see what happened. And I'm sure some of you, hopefully many of you, kind of noticed that they were equal, but they were equal to the one in the different order. And that's kind of what we have right here. All right, so another example of showing a property is true, but when it comes to transposes of products, we can take their transposes individually, but the order flips around. And in fact, we needed that just to make the sizes work. All right. Any questions about this or about, any of these properties? All right, I'm going to put a pin in this one. Feel free to answer that question, but we'll see a little bit more of that later on. And same thing with that one. All right. So let's assume for the moment that A is invertible. So what do you think the inverse of K times A is going to be? couple people seem to be, a few people are answering that this appears to be 1 over k times A inverse. Okay. Right. So, if 3 people out of 140 people are saying that it's equal to this, it must be true. Anyone want to come up with a reason for this one, or maybe a different possible answer? Right, so how would we show this? How would we show this? Determinants can't show inverses even if we had talked about determinants yet. Some people are saying it seems to have something to do with an exponent property, but technically we're actually proving that the exponent property works, so chicken and the egg. So we can't use that. That 1 over AD minus BC thing is only for 2 by 2s. And that would be part of the inverse. It wouldn't multiply by the inverse. How do we show something's the inverse again? I think we did an example where we showed something was the inverse. What did we do to show something was the inverse? What did we do to show something was the inverse? I think it was this example. Yeah. We show something's the inverse by multiplying them together and showing it's equal to what? Showing it's equal to I. So let's do that. K times A times 1 over K times A inverse, and the other way around, 1 over K times A inverse times K times A. Can we just multiply these together? K times 1 over K? Wait, doesn't order of multiplication matter? Ah, that's right, they're constants. So yep, we could say this is K times 1 over K, A times A inverse. So yes, we can absolutely switch the order of the constants, not matrices, but of the constants. So K times 1 over K is, it's 1. A times A inverse is I, and hence that's equal to I. Same thing over here, that's also 1 times I. So yeah. So technically what we've shown here is that if we have a constant multiple, with one exception, if we have a constant multiple, then the -1 can be thought of as being brought down in front of each exponent. So we're kind of seeing that the inverse is thought as a -1. We're seeing a lot of exponent rules making sense. And that's good. We want them to make sense. All right, we're not going to prove all of these, but there's a couple more that we have. The inverse of A transpose. What's the inverse of A transpose? These are just some properties that were talked about. I just want to make sure that we've seen this one. This one's kind of boring, but what's the inverse of A transpose? Yeah, it's the transpose of A inverse. So it seems like I'm just moving things around here, but what this is really saying is that if we wanted to find the inverse of A transpose, if we already knew what the inverse of A was, we could just transpose that answer. Assuming that it's these are invertible, what is AB inverse? This is the one we got to be careful about. What's the inverse of AB? I go over the proof of this in the videos, but yeah, this is B inverse A inverse. Yeah. So like with transpose, you can take the inverse of a product, assuming they're invertible, but the order again switches. And because matrix multiplication is not commutative, the fact that the order switches, we have to be careful about, because in general, this is not equal to this. Could you write it as BA inverse? And that would be A inverse B inverse, which wouldn't be the same thing. So the unfortunate reality of matrix multiplication is, except in some rare circumstances, we can't just assume we can change the order around. These are just a couple more properties of inverses. Again, they're proved in the videos, or at least the second one was proved in the videos. I encourage you to give this one here a try as well. Right, so any questions about these inverse things? I know we don't have a way of finding inverses yet. We're going to. But some of this inverse stuff or transpose properties. All right, so give this question here a try, kind of lumping all of these together. I'm not sure what you mean actual examples. Like I suppose, yeah, that's 3i. I mean, if you want, feel free to take any matrix A and a matrix B and then just, find both sides of the equation and see that they're equal. But that's not really an example of it. So I had a few people asking me about a similar example in the suggested exercises. So we'll kind of go over this together. So we want to solve for A here, which means we're solving an equation, so we kind of want to undo the operations that we've performed. So how do we get rid, and this is a weird way of phrasing it, but how would we get rid of the inverse? Well, can we just, right, we're going to inverse the inverse. So we're going to take the inverse of both sides. Oops. Didn't actually take the inverse of the left-hand side. So what does taking the inverse of the inverse do? What does taking the inverse of the inverse do? Yeah, it cancels them. So technically, there's a property that we're using here that B inverse inverse, that the inverse of the inverse gives you what? Yeah. The inverse of the inverse just gives you the original matrix. Again, assuming that it's invertible. but the inverse of the inverse gives you the original matrix. All right, in other words, A would equal to the inverse of 1, 2, 3, 4. And then how do we get rid of the plus 3i? Yeah, same way you did it whenever you started doing algebra. You want to get rid of addition, you do subtraction. And so we've solved for A. It's the inverse of 1, 2, 3, 4 minus 3 times the identity. So technically, we used a property of inverses in there, but matrices can work with the exception of a couple of our properties. We can solve for matrices in equations. Somebody asked me in an email a week or so ago, there's a suggested exercises that put a matrix inside a polynomial. And that makes sense. We can square matrices, just multiply it by itself. We can add constants. So matrices can go inside polynomials. Matrices can go inside equations. So a lot of the things we can do with numbers, we can do these with matrices as well. No, this isn't quite the final answer. I was giving people a chance to catch up. All right, so now that we have this is a 2 by 2 matrix, so we have a formula for that. So what is the inverse of 1, 2, 3, 4? That's the transpose, not the inverse. So 4, so that thing said you just flip the diagonal entries, negatized the off-diagonal entries. Then there was something out front here. Yeah, it'd be 1 over 4 minus 6, so 1 over negative 2. That's what, negative 2, 1, 3 halves, negative a half, and then just more matrix computations. Yeah, so again, technically the new thing here was the property that we can get rid of an inverse in an equation by taking the inverse again, using the property that the inverse of the inverse cancels off and takes you right back to the original matrix. Questions about this example? It was 3 times I. So the identity, so that would be 3 times 1, 0, 0, 1, 3 times the identity. And then that's just scalar multiplication of a matrix. You multiply every entry by 3. The last entry was negative 7 over 2. Assuming my, fraction subtraction. Why do we multiply by negative 1 over 2? That was the formula we saw right here. So that's the AD minus BC. I'm not sure what you mean by, how do you find the inverse without the formula? Is that the question? How do you find the inverse without the formula? Yeah, it only works for 2 by 2 matrices. Yeah, so how do you find it without the formula? Well, that's a wonderful question, which brings us to section 1.5 about elementary matrices. All right, so, first of all, just, I don't know if 1.5 was in the pre-lecture videos for this. So, what is an elementary matrix? What is an elementary matrix? Right. So, we are technically a little bit ahead of the schedule. So, hence, so an elementary matrix is is the identity with one elementary row operation applied to it. So I go over this in more detail in the pre-lecture videos, which I know I'm assuming most of you haven't taken a look at yet because it wasn't on the schedule for today, but I do want to spend a little bit more time on 1.5 than was in the schedule, so I will talk about it here. But it really is a fairly simplistic matrix. You start off with any size identity you want, and then you apply one row operation to it. So for example, take I3, the 3 by 3 identity matrix, and perform this row operation to it, and what do you get? What do you get if you take the 3 by 3 identity and you perform row 3 minus 4 row 1? What matrix do you get? Row 3 becomes negative 4, 0, 1. What about row 1 and row 2? Stays just like any time. You perform one row operation, it only ever changes one row unless you do the swapping 2 row operation, in which case it changes 2 rows. All right. So my next question was, what if you took 1, 2, 3, 4, 4, 9 and performed the exact same row operation? Which is something we did in section 1.1, technically. 0, 1, what's 0, 1? Row 3 changes to 0, 1. Again, row 1 and row 2 aren't changing because our row operation is only affecting row 3. So the key question about this that makes elementary matrices so powerful is what would happen if I took the answer to the first one and multiplied it instead of doing the row operation. What if we multiplied it? What do we get? row 1 times 1, 3, 4. Well, since row 1 is just the identity row 1, it's not going to change the first row, first column entry. 1 times 1 and zeros. Same thing, row 1, column 2. Same deal. It just picks off the first row and doesn't change it. If we took row 2, same thing. This is the second row of the identity, so it's not going to change the second row of our answer. As for the third row times the first column, well, what does that do? That takes -4 times 1 and adds it to just the 4 that was already there. In other words, it takes -4 times the first row entry and adds it to the 4. Exactly what the row operation did. And then similar, -4 times 2, and we get the exact same thing. In other words, the point is row operations and matrix multiplication are connected. So any row operation can be thought of as matrix multiplication. Now you probably are thinking this, you might be thinking this. If you're not thinking it, you should be thinking of this. Is why on earth would we do this? Row operations is easier. But that's not the point. The point is we're trying to come up with a method for what? What are we trying to come up with a method for? Based off the last section. Yeah, we want to find inverses. And inverses is a matrix multiplication thing. And we've come up with an idea that says matrix multiplication and row operations are connected. In other words, our method is going to use row operations to help us find the inverse. And that's what we're going to be doing. So instead of having to guess and check matrices to multiply, we're going to use row operations to help us. So that's the idea of what elementary matrices do. All right, anyway. Meta theory aside, let's just, go back to practice with some of these elementary matrices. So here are 3 row operations. Here are 3 row operations. So what I want you to do is to, first of all, figure out what the row operations are, and then come up with the 3 elementary matrices that correspond to those row operations. All right, some people have popped off at least the row operations. At least we got the row operations here. So what would be the first elementary matrix, corresponding to row 2 minus 3 row 1. What's going to be that first elementary matrix? No, we need to apply the row operation to it. So it starts with the identity matrix, but then we apply that row operation to it. So 1, 0, negative 3, 1. So that's E1. What about E2? Here's where things you have to be a little bit careful. So what do we get for E2? So it's 1, 0, 0, negative a half. And this is the question that tends to come up. So an elementary matrix, any elementary matrix, is starting with the identity and performing one row operation to it. So E1 is take the identity and perform this row operation to the identity. But if we're moving on to E2, we're not doing a row operation to E1. What happens if we took a row operation to E1? Is that an elementary matrix? If we performed a row operation to E1? No, why not? Why wouldn't that be an elementary matrix anymore? At least probably. Yeah, it wouldn't be the identity matrix with one row operation applied. It would be the identity matrix with two row operations applied. That's not an elementary matrix. So everything flies out the window. So for a new elementary matrix, you always go back to the identity. You perform the row operation to the identity, not the previous elementary matrix. Then E3, again, the identity with the third row operation applied to it. So that's how we find E1, E2, and E3. So the big point is, let's call this matrix A. So what is E1 times A? So what is E1 times A going to equal? Based on what we talked about in the last example. What's E1 times A? Yeah, it's this matrix right here. That matrix right there. 1, 2, 0, negative 2. Now what happens? Matrix multiplication is associative, so I don't need the brackets. What if we multiplied again by E2? What do we get? That performs that row operation. We get this. And what happens when we multiply by E3? We get 1, 0, 0, 1, which of course is the identity. And now we have a matrix multiplied by A that gives us the identity. So what have we found? I mean, we'd have to check the other side. Careful with my ordering. We found the inverse. So we found a way of finding the inverse as a composition of these elementary matrices. Now again, we probably don't want to find 3 matrices and multiply them together, but remember that these elementary matrices represent row operations, which means that we can find A inverse by using these row operations corresponding to these elementary matrices. And that's where we're going to pick it up on Tuesday. If you have any questions about this, please do let me know. If you have any questions about your test this upcoming week, also, please let me know. And I strongly, strongly recommend people read that course outline about what you can and cannot do during the test, because I'm already having to write 3 academic dishonesty reports for my other class. I don't want to start writing them for this class. Have a good day, everybody.